The next thing we want to show is that indeed with a scalar product you get all the other features that we've been studying before. So in particular, we will see, we don't know yet, that with a scalar product you automatically get a norm, and we kind of have the idea how these two things are connected to each other just by experience from R to the n. I mean, we know that the norm of an element x is connected to the scalar product like this. When you compute the scalar product of an element with itself, then you get the norm squared. So you could just take the square root of this and call this a norm. And this is indeed what we will do. And then the metric d of x comma y is, as we know, just induced by the norm via norm of x minus y. And then you could even rewrite that as the square root of scalar product x minus y with itself. Okay, so we already know that norm induces metric, and whenever you have a metric, then you have all the other stuff like convergence, Cauchy sequences, closeness, completeness. What we still have to show and will show is that with a scalar product you indeed get a norm, and the definition will be this. To see that this is indeed a norm, we need to check the norm axioms. The first axiom was the norm of an element x is 0 if and only if it's the x vector. So 0 is the norm of x, which is in our case defined as the root of scalar product x comma x. Holds clearly if and only if the term underneath the root is 0. But we know from our scalar product axioms 1 and 2 that this holds if and only if x is the 0 vector. So indeed norm axiom 1 is fulfilled. To see norm axiom 2, recall this is the norm of alpha x equals modulus alpha norm x. We just fill in our definition. So this is square root of alpha x times itself in the scalar product. Okay, and now you have to recall how the scalar product deals with little alpha. So this little alpha comes in front just as little alpha, and we just check that that little alpha comes in front of the scalar product as little alpha bar. So what we get here is the square root of alpha times alpha bar x comma x. Now we all know what alpha times alpha bar is. This is just the modulus of alpha squared. And of course you can drag that one out of the square root as just modulus alpha. So this gives us modulus alpha times square root of x comma x. Okay, but this is just our definition of norm x. So indeed, also this norm axiom is fulfilled. It remains to check the third one, and this, well, we know it is usually the trickiest one, triangle inequality. So the norm of x plus y has something to do with the norm of x plus norm of y. When we bridge this gap in our proof, we are allowed to use this sign in between. Let's just recall this, but we are not ready for this yet. By the way we define our norms, we use these square roots, and to avoid unnecessary technical stuff, let's just look at the square here, and therefore of course the square here, and then we can avoid the root. So we can just write this as scalar product of x plus y by itself, and then use the third property of scalar products to just get this rewritten as x comma x plus x comma y plus y comma x plus y comma y. By symmetry, we can recognize this as x comma y complex conjugate, and of course we know that this one here is just norm of x squared, and that one is norm of y squared. Now, adding a complex number and its complex conjugate, what do you get? Well, you get 2 times the real part of that complex number, which in our case is scalar product of x and y. Right. Okay, now at this point we don't quite know how to continue. So how about starting from the finish line and going backwards until we hopefully meet? Okay, this one is easy. This is just norm of x squared plus norm of y squared plus 2 times norm of x times norm of y. Okay, and that's not too far away from what we have before. Okay, we can estimate the real part of any complex number by just the absolute value of that complex number. So let this be our next inequality. So we just say that this is less than or equal to the modulus of x comma y. Okay, so we should at least write it once properly. So this is less than or equal to norm of x squared plus norm of y squared plus 2 times modulus of x comma y. Okay, well, if we compare what we have, we see this part is here, that part is here, also the 2 is there. So the only thing that needs to be shown is that this modulus of scalar product x comma y is less than or equal to this norm x times norm of y, and that would complete the proof. Okay, and to see this we need the so-called Cauchy-Schwarz inequality, which says exactly what we need. It says that for 2 vectors, you always have that the norm of scalar product x comma y is less than or equal to norm of the first vector times norm of the second vector. So if we had this inequality at our hands, and we will have that soon, then our proof would be finished. You will find the Cauchy-Schwarz inequality on our first problem sheet, and yeah, you will be asked to prove it, and there will also be hints. And once we've proven the Cauchy-Schwarz inequality, then we can finally tick this one off and say, yes, give me a scalar product and you have all the rest. And that's what the starting point for Hilbert spaces will be.